There is a place in the cosmos where God's laws are broken. A place where gravity, the force that holds galaxies together, becomes an all-consuming tyrant. A place where time itself unravels and space collapses into an impossible point. They are the universe's ultimate predators, the silent ghosts that haunt the void. They are black holes. For decades, they were the stuff of mathematical nightmares, a bizarre prediction of Einstein's theory of relativity. Today, we know they are real. We have photographed their shadows. We have heard the gravitational echoes of their cataclysmic collisions. But the most profound and terrifying question remains. What happens if you fall in? What lies on the other side of the point of no return? Prepare yourself, because today we are taking the most dangerous journey in existence. We are crossing the event horizon and plunging into the heart of the universe's greatest enigma. To understand what's inside, we must first understand what they are. A black hole is not a hole in the traditional sense. It is an obscene amount of matter crushed into an infinitesimally small space. Imagine taking a star 10 times more massive than our Sun and compressing it into a sphere the size of New York City. The result is an object with a gravitational field so powerful that it warps the very fabric of space-time around it, creating a well from which nothing can climb out. They are the stellar corpses left behind after the most massive stars die. When a giant star exhausts its nuclear fuel, it collapses under its own immense weight in a cataclysmic explosion called a supernova. The remnant core can become a black hole, the most extreme object in the universe. The journey into a black hole begins at its edge, a boundary with a name that is both poetic and terrifying: the event horizon. This is not a physical surface. It is a mathematical line in the sand, the point of no return. It is the distance from the black hole's center, where the escape velocity exceeds the speed of light. Before you cross the event horizon, you still have a chance, however slim, of escaping if you have enough thrust. But the moment you pass it, your fate is sealed. Every possible path you can take, even if you try to accelerate away, will inevitably lead you toward the center. Inside the event horizon, the future is not a time, it is a place. And that place is the singularity. But what would you actually feel as you fall? The answer depends on the size of the black hole. If you were to fall into a small, stellar mass black hole, you would be killed before you even reached the event horizon by a brutally named process called spaghettification. The tidal force is the difference in the gravitational pull on your feet versus your head, would be so extreme that your body would be stretched into a long, thin strand of atoms. A quick and grotesque death. However, if you chose a supermassive black hole, like Sagittarius A** at the center of our Milky Way, the experience would be far stranger. The tidal forces at its event horizon are much gentler because its horizon is so far from the center. You could, in theory, drift across the event horizon without feeling anything unusual at all. You would be alive, conscious, floating in what appears to be normal space, but you would be doomed. And this is where Einstein's relativity reveals its most bizarre face. To a distant observer, say, your friend watching safely from a spaceship, something very different would happen. As you approached the event horizon, your friend would see you move slower and slower. The light from your body would become redder and redder, a phenomenon called gravitational redshift. Your image would appear to freeze at the edge of the black hole, slowly fading over an eternity but never actually crossing. To your friend, you never went in. But for you, your journey inward continues, and time begins to warp. Looking back out, you would see the entire future of the universe flash before your eyes. You would witness stars being born and dying, galaxies colliding, all in a matter of moments. And where are you headed? To the ultimate destination for all matter that falls into a black hole, the singularity. This is the true heart of the mystery. According to Einstein's general relativity, the singularity is a point of zero volume and infinite density, where all the black hole's mass is concentrated. It is a place where the laws of physics as we know them, including Einstein's own theory, simply break down. Space and time cease to have meaning. It is the end of the road, the final stop for reality. What happens at the singularity is, quite literally, unknown and perhaps unknowable. It is the universe's ultimate 400 for not found error. But modern physics dislikes infinities. They are usually a sign that a theory is incomplete. This is where quantum mechanics, the science of the very small, clashes with general relativity, the science of the very large. To truly understand the singularity, we would need a theory of everything, a theory of quantum gravity that unites these two great pillars of physics. And that theory doesn't exist yet. However, it gives us some mind-bending, speculative possibilities. One idea from string theory is that the singularity is not a point, but a fuzzball, a tangled ball of vibrating energy strings. In this scenario, information that falls into the black hole is not destroyed, but is scrambled and stored on the surface of this fuzzball. Another theory, from loop quantum gravity, suggests the singularity is not an end, but a beginning. It proposes that matter is crushed to an incredibly dense, but not infinite, state and then bounces. The black hole would become a bridge, a wormhole, to another place in our universe, or, more exotically, to an entirely new universe. The singularity would be the big bang of a baby universe. The idea that our own universe may have been born from inside a black hole in a parent universe is one of the most dizzying possibilities in modern cosmology. And what about information? A fundamental law of quantum mechanics is that information can never be destroyed. But if a black hole swallows a book, the information within it seems to vanish forever. This creates the famous black hole information paradox. Stephen Hawking shocked the world by proposing that black holes are not entirely black. Due to quantum effects near the event horizon, they emit a faint form of radiation, now known as Hawking radiation. This means black holes very, very slowly evaporate over trillions of years. But if they evaporate, what happens to the information that fell inside? Is it destroyed, violating the laws of quantum mechanics? Or does it somehow leak out, encoded in the Hawking radiation? This is one of the greatest intellectual battles in theoretical physics today. The leading solution, the holographic principle, suggests that all the information about what fell into a black hole is somehow encoded on its two-dimensional surface, the event horizon, like a hologram. Black holes, therefore, are not just astronomical objects. They are theoretical laboratories that force us to confront the absolute limits of our knowledge. They are the meeting point where gravity, space, time, and information exist in their most extreme forms. They teach us that reality is stranger, more flexible, and more mysterious than our intuition could ever conceive. They are proof that the universe still holds secrets that are beyond our imagination, hidden in the darkness at the heart of a gravitational monster. The journey into a black hole is a one-way trip into the unknown, a plunge into the abyss where science becomes philosophy, and the questions become more important than the answers. What do you think lies inside a black hole? A singularity, a bridge to another universe, or something we can't even imagine? Leave your wildest theory in the comments. And if you re-fascinated by the great mysteries of the cosmos and want to keep exploring the frontiers of knowledge, subscribe to the channel and hit the notification bell, because the universe is full of enigmas waiting to be unraveled. Until next time.